Welcome back to the afternoon session of the meeting. And now we will have the pleasure to introduce Laura Becerra. She will tell us about simulations of the induced gravitational collapse. So Laura, please feel free to share the screen.
You can see my screen?
Yes, we can see the screen.
Okay, hello everybody. Well, as I was told, I'm going to talk about the small particle aerodynamic simulations of the induced gravitational collapse. This has been a work done with the Ethernet collaboration since like 10 years ago for now. So this is the outline of my talk. I will talk about a little bit about the induced gravitational collapse model, describe you the simulations, and then talk about the result and the observational consequence we can obtain with the simulation. So the induced gravitational collapse model was a model introduced to point a binary origin from the GRBs and with the long GRBs associated with supernova of time 1, B, and C. This model is progenitor of this model is a binary star or two main sequence stars. The most massive star will collapse first and will leave a neutron star as a remnant. So the system will be formed by a neutron star and the secondary main sequence stars. And these two stars, if they remain bounded, they will interact each other through phases of Roloff overflow and common envelope phases. And in this way, the main sequence star will lose its hydrogen and helium outermost layers, and the system will be formed by a carbon-oxygen core and the neutron star. And when this carbon-oxygen core go to the end of its life, a collapse in a supernova, the material ejected in the supernova will be gravitational attracted by the neutron star companion, and different outcomes of the system can be obtained. And this, the ejecta will trigger a hypercritical accretion to the neutron star, and if the system is enough close, the accretion on the neutron star could be enough high to make the star reach its critical mass and collapse in a black hole with the emission of a GRB. In this scenario, we have called the binary driven hypernova of type 1, and if the system remains bounded, it will be formed by a neutron star that will be the remnant of the collapse of the carbon-oxygen core and the black hole that will come from the collapse of the neutron star companion. This system is characterized for energy greater than 10 to 52 Earth. And in the other scenario, the system is not so close, so it will be an accretion on the neutron star, but this is not going to be enough to lead to its collapse. So if the system remains bounded, we will have a binary system of two neutron stars. We call them, in this case, a binary driven hypernova of type 2, and these systems are less energetic. So what I'm going to show you is the simulation of the last phase of the system that will be the expansion of the material of the supernova and the accretion on the neutron star. So we're going to simulate this scenario, and we're going to make a initial parameter study to see how or in what condition is possible that the neutron star companion or the remnant from the collapse of the carbon-oxygen core collapse in a black hole. So we're going to evaluate the effect of the progenitors of the carbon-oxygen cores, the energy of the supernova, the initial mass of the neutron star companion, and the period of the orbital period of the initial binary. We got done this simulation with a small particle aerodynamic code developed at Los Alamos by the group of Fryer. And in this kind of code, basically the fluid is free, that it is formed by many particles. Each particle, it will be characterized by a mass and a position and velocity and a smooth layer. And with this parameter, all the other physical quantities like the density, pressure, temperature can be interpolated. And in this way, we can solve the aerodynamical equation for each of these particles. And yes, and also in order to model the induced gravitational collapse, we have introduced in the simulation 2 point particles that will be modeling the neutron star and the new neutron star. And these point particles will be interact gravitationally with the other particles of the fluid, but no aerodynamical. And this particle can also accrete other fluid particles if they follow 3 conditions. If the particle is inside some accretion radius, it's gravitationally bounded to the point particle, and it's not circularizing around the particle. So if some fluid particle fulfill this condition, we remove it to the simulation and add the mass, the angular momentum, the linear momentum to the point particle quantities in order to conserve these quantities. And for the initialization of the simulation, we model the collapse of the carbon-oxygen core with a 1D core collapse code. And when the supernova choke reach the star radius, we map this simulation to a 3D SPH initial configuration, put this progenitor in a binary orbit to the neutron star companion, and run the simulations. So we have worked with many progenitors for the carbon-oxygen core. Here are the masses at the 0s main sequence star. So they will have different properties and the moment of the collapse of the carbon-oxygen core. So here I will show you one of the simulations. This simulation was made with a carbon-oxygen core progenitor of 25 solar masses. The progenitors, when at the moment of the collapse, will eject around 5 solar masses and leave a new neutron star of 1.85 solar masses. We had put this progenitor with a neutron star companion of 2 solar masses, and the initial orbital period of the system is around 5 minutes. This is a small orbital period, and it's the minimum orbital period that the system can have in order that there's no Ross-Love overflow before the collapse of the carbon-oxygen core. So here there are some snapshots of the density on the equatorial plane at different times. So we see here the ejecta material from the supernova, and some of this material has been attracted by the neutron star companion and formed like a tail behind the star. And with time, it starts to form a disk around the neutron star companion. And this time also on the new neutron star, there is full bar accretion of the material that has not enough kinetic energy to escape from the gravitational field of the new neutron star. But also at some point, this new neutron star, we start to attract the material that was captured by the neutron star companion. And also we will have a disk around this star. So here this 3D visualization of the system, and we see the close of the binary star. The material is highly asymmetric. It's not the initial spherical expansion that we have. The presence of the neutron star induces some asymmetries to the expansion of the supernova material. And also we can confirm here that the material around the star form a kind of this follow a Keplerian profile close to the new neutron star and the neutron star companion. And with the simulation and from the particle list, the mass from the particle that has been accreted, we can calculate the mass accretion rate from both of the stars. So here we see in blue the accretion rate of the new neutron star. We initially have some 4-bar accretion rate, but this decreased rapidly with time. But at some point, this starts to stabilize, but because this starts to acquire material from the neutron star companion. And also in red, we see the accretion rate from the new neutron star. We have a peak, that is when the innermost layers of the supernova reach the neutron star companion, and it starts to appear from the disk. And if we see these accretion rates are high, they are of the order of 10 to minus 3 solar masses per second, and these accretion are possible because around the neutron star, it forms an atmosphere that is enough dense and hot that the emission of neutrinos start to be efficient and can release the gravitational energy from the accreted material. And for this scenario, the most efficient process to emission of neutrinos is the electron-positron annihilation. And well, with this, we can now start to change the initial parameter of the system in order to evaluate how the influence will to the evolution of the system. So for example, here there are some accretion rates. In this left plot, we have changed the supernova energy, the kinetic energy of the supernova. We see with this eta value that correspond high eta value correspond to high energy, and low eta value correspond to less energy. So we see that the amplitude of the accretion doesn't change with the change of the energy from the supernova, but the shape of the accretion changes. So we're going to have that for a less energetic supernova, the star will accrete material at high accretion rate for longer times. And here at the right, we see the change of the accretion, but with the orbital period of the system. So in this case, we see that the accretion rate is like similar from different orbital periods, but it decreases if the orbital period increase. And here we see the effect on the accretion rate on the new neutron star, the remnant from the collapse of the carbon-oxygen core. And as I expected, if we change the energy of the supernova, initially we don't see any effect. We just see that the 4-bar accretion, but at late times, this bump that corresponds to the accretion when it starts to accrete material from the disk of the neutron star companion, this bump increase its amplitude, and it happened early in time for less energetic supernova. And we see the same effect and in the last cases with the changes on orbital period, we just see that initially we have the 4-bar accretion that is almost independent of the initial condition of the system. But we see that the accretion decrease, or this late bond decreases with the increase of the orbital period. And here there are more snapshots of the density on the equatorial plane from different energy of the supernova. We see that if the energy is too high, the material will not be captured by the new neutron star, and we don't going to see any kind of this, and the accretion will be really small. But if this energy decrease a lot, we have seen that the material or high density of the material is accreted by the binary system. So now with this simulation, we can address the question whether the neutron star will collapse or and form a black hole due to the hypercritical accretion it have happened. So for this, we need to follow the gravitational mass of the neutron star, but also the angular momentum of the neutron star. So we're going to assume that the accretion rate we have calculated from the simulation will contribute to the baryonic mass of the neutron star. And also I'm going to assume that the accretion occurred by a disk. So the angular momentum that the star will be accreting will be the angular momentum of the last stable orbit of this disk. So to solve these two equations, we have used the fifth formula of the solution of the uniformly rotating star from Chipoletta. And we also going to assume that the star evolved through a stable state or uniform rotating configuration. So here we see two evolutions in the plane of the star and angular moment, or the star mass and angular momentum. And we see, for example, if the accretion rate of the, if the star accrete angular momentum efficiently that correspond to the red line of this plot, both star, the new neutron star that is the dashed line, and the solid line is the neutron star companion, both stars will reach quickly the mass change limit. And this means that they're going to rotate so fast that the material at the equator will be rotating faster than a particle in a Keplerian orbit. So probably the material will start to expel this matter that rotate faster, but we don't know if this can lead the star to a collapse or just to come back to an unstable configuration. But if this accretion of angular momentum is not so efficient, there are some losses of angular momentum through jets or something else. The stars in both cases, in this case, they're going to reach the secular stability limit. And in this case, we know that this limit, the star is unstable to axially symmetry perturbation. So later on dynamical time scale, the star will collapse to a black hole. So it is possible that the star collapse, and this happens for a short orbital period and low energy for the supernova. Okay. Also, with this simulation, we can calculate the rotational power of the evolution of the supernova from the accretion of angular momentum. And we see that this luminosity will be characterized for two peaks that correspond to on the accretion rate of the new neutron star, that correspond to the initial four-bar accretion and the late accretion from the disk of the new neutron star. So this first piece is going to be equal or going to be almost independent of the initial orbital period of the system, but this second piece will happen early and it's going to depend on the initial orbital period. Going to be greater for short orbital period and smaller for longer orbital period. But we also, apart to these two peaks, we're going to have a peak from the accretion rate of the new neutron star, and this peak will depend from the period of the system, but also the initial angular momentum of the new neutron star. But we can relate this luminosity with a early prone emission of the GRBs as an hypothesis. Also with this kind of simulation, we can address the question whether the binary system remain bounded or remain unbounded after the supernova event. And usually when it's assumed when a supernova event happens in a binary system, if the material ejected by the supernova is more than the half of the initial mass of the binary system, this system is assumed that it remains unbounded. But in the case of the binary driving hypernova initial binary system, this assumption doesn't apply. And for example, we see here that dependent of the energy of the supernova, but for many cases, we have that the system lose more than the half of the initial mass of the binary system. And in all these cases, the system remains bounded. And this is because we here treat with short binary periods, so more or less the time scale of the orbital motion and the time scale of the supernova expansion is more or less of the same order. So with the assumption of the other statement doesn't apply to the system, and also we're going to have accretion on both stars, the neutron star and the neutron star companion, and is accretion of high order that cannot be neglected. So we can also calculate the maximum orbital period that the system will going to remain bounded, and as is expected, this maximum orbital period will going to depend mainly of the initial energy of the supernova. And finally, we can relate some GRB observation. For example, here on the left, we have a GRB that has been classified as a binary driving hypernova of type 1. This means that in this case, we're going to have the collapse of the neutron star to a black hole. And here on the right, we have an example of a GRB, of a binary driving hypernova of type 2, when as an outcome, we're going to have 2 neutron stars. But for both cases, the afterglow of this GRB can be related or can be fitted with the rotational power of the new neutron star, and some inference can be made about the magnetic field of the neutron star and the initial orbital period. And with this initial orbital period, we can relate the initial orbital period of the new neutron star with the orbital period of the binary system. If we assume that the angular momentum is conserved and is locked with the orbital period of the neutron star with the orbital period of the binary system. And for this GRB, the one on the left, we can associate a system of around 4.4 minutes, and the one on the left, we can associate a system of around 11.8 minutes. And the relation of both systems is around of the order of 2, and is consistent with the simulation that tell us if we increase a lot the binary orbital period in the initial binary system, the neutron star could not collapse to a black hole. So this is a summary. We have talked about the simulation. I have described you the small particle hydrodynamic simulation and explore different parameters of the initial system. We have determined whether it's possible that the neutron star collapse or not, and we have made some observational inference. So thank you very much. I cannot hear you.
Okay, probably there was a problem. You couldn't hear me. Okay, thank you very much for your nice talk. And now we have time for questions or comments. So, are there? Okay, yes, there is some questions.
Well, needless to say, this work has been extremely important and has been used particularly in the recent paper by Wang Yu to explain the beautiful new result of 1908-29A, where we really see the spinning up process due to fallback, both of the accretion of the supernova on the companion neutron star and on the new neutron star spinning it up. And we have used extensively all your simulation. And tomorrow, Wang Yu is going to present this. And of course, the cases that you have shown also are very important. But the new point is really to understand the new role of the triptych, or the triptych which is composed of the CO core collapse generating the supernova, almost standard, and then the different accretion on the new neutron star generating the afterglow, and on the black hole generating all the high energy radiation. And everything fits remarkably well, and is possible to identify the mass of the black hole and the mass of the new neutron star and their relative spin. And this has been made possible thanks to the work you have done, Laura, together with Freya. And of course, Rueda, who has been guiding all this. Congratulations again.
Thank you.
Okay, so are there any other questions or comments?
I would like to add a comment, if possible.
Yes, of course.
Yes, about one of the important points, actually in the mediation picture, is that we expect to be implemented soon is the population synthesis models for the binary evolution. And that's the reason why we are making this effort with Laura in constructing these latest results about the binaries that remain bound and all these fitting formulas of this binding energy, or what is the final period of the binary after the explosion, and all this kind of thing as a function of the supernova explosion energy, or as a function of the initial orbital period, or in doing this study and constructing this kind of analytic fitting formulas that eventually can be used or can be incorporated into population synthesis model codes. So this is just to make this comment about this. We expect to be implemented by someone because we don't have this kind of codes, but we are looking very much forward to this future implementation soon.
Thank you, Jorge, for your comment and further discussion. Are there any other questions or additional comments or remarks? Okay, so if not, we thank Laura again. And now we have, in the schedule, we have a break until 5 p.m. Central European time, and then we will have the general discussion. So see you in a bit. Thank you.
Okay. I see Chris Fryer online. Chris, can you give us a talk tomorrow?
Yeah, I was just writing Jorge about that. Maybe as people, I don't want to, I guess people are taking a break right now so we can discuss this. What would you want me to talk about? I see that you had a talk on Ultrasat. There's another proposed mission in the US called CyBEX, which is kind of like an Ultrasat, but has a lot of other features. It gets spectra and it gets X-rays. And that might be something that would be interesting because it would be neat to see what you all thought, if that could be useful for some of these observations. I could also talk about using standard progenitors for long duration gamma ray bursts, how if you look at the collapsar progenitor, what predictions does it make for high redshift? I just did a study for that for GAMOS, the GAMOS satellite. So I could talk a little bit about the GAMOS satellite and what it's planning to do. Do you guys have a preference on what you want me to talk about?
Well, anything both of them seems very interesting. Maybe you can mention both of them. And at the same time, tomorrow morning, Liang Li will present some interesting result. And maybe if you can participate later in the discussion, we will discuss a little bit about the dependence of the observation with Z, which of the GRB, which also is very new, and we would like you have some of your feedback on this.
Yeah, so I apologize for not making more of the meeting. I came back from vacation and managed to get sick, so I'm just getting better from it. So I haven't I missed most of the meeting, but tomorrow I'll definitely be more present.
Okay. Jorge, any comment?
No, it's okay. Just thank you, Chris, for reacting promptly to my message. Yes, I agree that both topics are relevant for us. So it will be if Chris doesn't mind to treat both of them, if this is not a problem for you, we would like to hear about both of them.
And how long of a talk do you want? Is it like a 30-minute talk, 20-minute talk?
45 up to an hour. 45 minutes up to an hour.
Okay. Yeah, I could probably give an overview of these the two satellite missions and how they tie to both the GAMOF mission and its ties to high redshift GRBs and the CyVex mission. That would be and see, that would be great to get feedback from you all on these missions.
Are you going to mention something about the three-dimensional models of supernova?
Would you like some? That's a different topic. But it'll be covered. Yeah, I will cover it some with the CyVex when I talk about CyVex, because CyVex is looking at three-dimensional features. So I can talk about. Let me have that be the main. I'll start with that, and then we'll see how time goes and how questions go, and I'll talk about the high redshift GRBs if there's time.
Okay. Thank you very much, Chris.
Thanks. Okay, then we can have coffee and get together around 5 o'clock. See you in a moment.
See you in a moment.
He had a really rough day, Phil. Started the day in the top 10, but lost 8+ minutes to Bego.
Welcome back, everybody. Now we are at the last session of today, and it is a general discussion related to this week, and also if you have general remarks on some topics that you would like to discuss from last week. So since Vae is here, I would like to point out some nice discussion that was brought it up by Massimo Della Valle this morning about the problem of the rate of the GRB supernova connection. So I was pointing out that, as you mentioned in your talk, Vae, it's important to address the problem from the point of view of selection biases. So if we do not correct for selection biases also the cases of the GRB supernovae, even though they are at a smaller redshift, when we consider at high redshift sources, then this effect may matter for the long GRBs. So I don't know, Vae, if you want to add something about that.
I really didn't understand what was the question. I didn't see the note.
Yes, no, it was related to, there was a talk by Massimo Della Valle, and there was a discussion about the GRB supernova rate at high redshift. So there were some concern by org and some mismatching of some computation of the rate. So my comment was that if we do not correct for selection biases, also for the case of the GRB supernova, we can have a mismatch between the star formation rate and the GRB rate. So I don't know if you would like to comment.
That's true. I agree with that you also have to take account selection biases and data truncation all the time, no matter what category you are looking at. But in case associated with supernovae, I guess they are mainly low redshift, so this selection biases are not as large
Critical.
as higher redshift. That's what I would say.
Yes, okay. Thank you so much for your remark. And I think Professor Ruffini wants to start the discussion about the modeling. So I will give the floor to Professor Ruffini.
Good, thank you. When we have had a few presentations, and we will continue tomorrow. But one of the most important points we like to illustrate, since Raim is here, can you please show one of the multi-component in 1901-14C?
Yes, a moment.
The slides, the global slides, which we will return again tomorrow, and maybe if Yerlan is there, if he can show again the summary, the two slides that you have shown at the end of your presentation. These are the three on which I would like to come back. Maybe Yerlan first show the two slides at the end of your presentation, and then we will ask Raim to show the one of 1901-14C.
Okay.
Maybe you can, I think yes, the last two. Yes, the last two.
This one?
No, the table, the one with BDHN1, BDHN2, BDH3. No, the one.
Yeah, I see. It's coming.
Okay, this one, previous one, yes, this one, and okay. I think the striking part which comes out of this presentation already this morning, and Massimo has commented, and we will keep commenting, is the fact that if you take practically all the supernova, independent of their energetic of the GRB, practically the luminosity of the supernova is constant, and the time of happening, the outer slides, is also practically constant. Therefore, the big issue show the luminosity, the time, the outer slides. The big issue is how can it be? Are you there? Can
Yes.
you show the outer slides?
Here is the peak time.
Yes.
The next one.
Yes, and one is the time of occurrence in the rest frame, and the other one is the luminosity, and they're practically constant. The big issue is going back to the BDHN1, BDHN2, BDH3 is how can it be that there is such an enormous difference in energy in the gamma ray burst? And for this, I am insisting, is the fundamental difference between the general approach, which is based on an idea that all GRB are practically from a source, one kind of source, a collapser, and with a standard jetted emission. Instead, the binary-driven hypernova model, and I would like to have now the picture of Moradi of the BDHN1, is that we are in presence of an enormous, more complex, and the one with the spectra, if you have, okay, that one. And we are in presence of a much, much more complex system in which practically you have this three component, the CO core, which collapse and create a new neutron star, the binary neutron star companion, and the supernova and the new neutron star. And the accretion of the supernova on the black hole give origin to the most energetic emission, which has two components. In the MEV first, which is the UPA phase, and in the JEV component, which is the power law emission. But this one has its own characteristic and comes out from the black hole, and the energy of this system is just related to the rotation of the black hole and to the mass of the black hole. And this has been the way that we have determined the mass of these systems. Analogously, what we have is that the accretion of the supernova into the new neutron star give origin to the X-ray afterglow. Therefore, this is the heart of our picture. In the case that the black hole is not present, then the UPA phase, the first phase, the UPA1 and the UPA2 are missing. And also the JEV radiation is missing. And we have only the accretion of the supernova into the new neutron star, which express the X-ray emission of the afterglow. And this is the picture that tomorrow will be shown by Wang Yu. Therefore, these are the two systems which shows the complexity of our approach and the energetic of this approach, and the reason, or the essential reason, of the different component. Now, when you go to the BDHN1 and you sum up the UPA phase and the JEV radiation, and then you sum up as well the X-ray afterglow, all these together comes out with the energy of 10 to the 54 erg. Therefore, in order to explain, but the supernova which give origin to the initial accretion is a standard one. This is the key point, but the accretion of the supernova into the new neutron star, which create the black hole and generate that energy, and the accretion of the new neutron, of the supernova ejecta on the new neutron star gives us to the X-ray afterglow. Now, if you sum this energy, which are due to the single supernova standard, okay, you end up with 10 to the 54. Like that, if you go to BDHN1, since the black hole is not there, you have just the afterglow in X-ray afterglow, and that is the one which pays for the energy of the BDHN1, which is much lower. This is the reason why we have made an enormous amount of work in study the UPE in all this, we should write a review explaining all this, because now all the results are practically obtained and published. And therefore, the solution, and in both cases, you have not a single jet like in the traditional approach, which has just one single object with a typical jet, ultra-relativistic. Here we have a system of jets. The jets coming out from the UPE phase, which are repetitive on time scale of 10⁻⁹ seconds, repetitive. And each one with a Lorentz gamma factor of the order of 200, lasting of the order of 2 seconds. And then you have the JEV radiation, which we discussed with Orge, and that one also has to do with synchrotron due to the extraction of the rotational energy of the black hole. And all the quantum effect about the UPE are also paid by the rotational energy of the black hole. This is a fantastic point. Therefore, we cannot afford the luxury to study GRB without looking at all these processes separately. And understand the GRB are by far the most complex system in the universe. But we need to analyze, we have to analyze each one of these features and see how they contribute to the overall picture. This is the key point. I hope that this will become clear as we go on. You have any question on this, maybe? Before I change topic?
I question, Remo, this multi-jet system. Are the different jets the same space, just only different times, or they're both different spaces too?
They are completely they are not a jet. They are all, okay. First of all, let's look at the one originating in the black hole, okay?
Yeah.
The one originating in the black hole, there are two phases. The UPE phase, which are changing, which vacuum polarization process, quantum electrodynamics over critical field, they act on time scale of 10⁻⁹ seconds. The black hole shoot and stop. Every time it stops, it loses part of the angular momentum, and until the angular momentum does not decrease to become undercritical, this UPE phase continue to work and emit the majority of the energy up to 10⁵ Hertz in these first 2 seconds, which you see there in blue.
Yeah.
Is that clear?
Yes, yeah, thanks.
Then after the blue phase, you start to have the JEV radiation, the JEV in red, okay? And that the JEV radiation comes from the synchrotron radiation emitted by the solution that we studied with Rued and with Royker about the synchrotron radiation into the magnetic field of the world solution. And this is the red part. Again, they are in that radiation comes along the rotation axis of the black hole. Is that clear or not?
Yes, so they are just physically different places, yes.
They are physically different places, a completely different time scale.
Yeah. Okay, thanks. Yeah, that's what I was asking.
Okay, now let's look at the new neutron star. The accretion of the supernova onto the black hole gives these two emissions, the UP phase and the JEV radiation. But the accretion of the supernova on the new neutron star generates the synchrotron radiation, which we studied in many papers, the synchrotron radiation around the new neutron star spinning down. And this is the afterglow. And each one has its own gamma Lorentz factor. I mean, the blue vacuum polarization have gamma of the order of 200, and they are jetted in this early phase, turning on and off from the black hole. The radiation in the JEV has a 60-degree opening angle along the rotation axis of the black hole. And the radiation instead from the new neutron star is a large angle emission with synchrotron radiation for the X-ray afterglow. And this radiation of synchrotron around the afterglow is a large angle emission of the order of 60 degrees or larger. Therefore, the three energetics sum up to 10 to the 54, but they are completely independent physical process. That makes sense to you? Do you this clarify? Why?
Yes, yes.
I don't know if Orge likes to add something.
Yes, hello. Well, I'm going to show some more details tomorrow morning about these early phases of a little bit more with respect to what Laura showed today. Some calculation that we have done in the, let's say, last month. Also need to show some specific results on a couple of GRBs about these early phases. About this possible also double peak structure of the prompt emission that we found in 19029A. How this is related with the two accretion episodes, one on the newborn neutron star and the other one on the neutron star companion. So just to highlight some of the points that I'm going to touch tomorrow, specific GRB observables, what are the specific physical processes ongoing starting from the supernova explosion, and what kind of physical processes this supernova is triggering in the system, and how they relate to the GRB observables. So, well, you may already you summarized already more or less all the points, but I'm going to detail some of them a bit more from the point of view of our simulations. So if you like that, me to show something now, just tell me. I can even show something if you like. But I will touch all these points tomorrow morning.
Both
so that will be that presentation will be morning time in Europe time.
Yes, my talk is planned at 9 a.m. Yes, yes, the first talk tomorrow morning. Well, but
Okay.
I'm glad to show something. If you, if you like to show something, I can even show that some whatever you like. I mean, the presentation is ready.
The key point, Vi, is the accretion on the black hole, and the energy is paid by the rotational energy of the black hole. The accretion of the supernova into the new neutron star, the energy is the rotational energy of the new neutron star.
Mhm.
And in both cases, you have synchrotron. Of course, in the case of the accretion on the black hole, you have completely different phenomena if the critical field is overcritical for percreation or undercritical. Undercritical is the jet at the Java emission. Overcritical is the UPE. And the characteristic of the UPE is time varying on very, very, very short time scale of the order of 10⁻⁹ seconds. This is completely new, that you have turning on and off, on and off, on and off on very short time scale. And the on and off, in every process, you lose part of the rotational energy of the black hole. And as soon as the rotational energy of the black hole goes under critical, the magnetic field, then you don't create vacuum polarization any longer, and you have jetted emission on the rotation axis. But it's essential to split. There is not a single jet. And even the jetted in the UPE have a gamma maximum 200. And again, the synchrotron are practically around the new neutron star, practically no gamma. You have just a synchrotron.
Also, one other question: is the optical afterglow from the accretion disk also?
Okay, good you ask a question, because I cannot go on without your question. Okay, now let's look at the afterglow. Can I go back to the afterglow picture a moment, Raim? And I want to show you the thing which to me is the most exciting. Can you show, Raim, the other slides here? Okay. Are you there? Vi, are you there?
Yes, I'm looking at it.
Now you have the afterglow in yellow, in X. You see in the X-ray, dark, okay? X-ray afterglow.
Yeah.
Are you there?
Yeah.
That is synchrotron emission. But at the same time, from that new spinning neutron star of the afterglow, are you there?
Yeah.
You have also the optical of the synchrotron and the radio of the synchrotron, which are relatively the orange there and the brown there. That are the optical, maybe Raim, can you point out?
Yeah, it's R band. I can see R band. And
okay, this one is just the optical of the synchrotron, and the radio is the radio of the synchrotron due to the afterglow. You see the point?
Yeah. Well, these are coming from different places or same place?
From the same place around the Orge can enter into that at any moment, But let me point out the key, the masterpiece, okay? The masterpiece. The masterpiece is how you can see the supernova in blue.
Yeah.
Okay? Because the energy, the luminosity is much lower than the afterglow. But the masterpiece of this work is that you don't care about the luminosity of the X-ray. You care about the luminosity of the optical. And as you can see, thanks to the existence of the synchrotron, the quantity which count is not the, and to the synchrotron, is not the X-ray luminosity, it's the optical luminosity. And indeed, the optical luminosity is below the supernova, and this is the reason why you can see it. I mean, this field is very beautiful and fantastic, but people have to study it. It's not a single jet. It's much more complicated. But the masterpiece is that you can see the supernova exactly because the new neutron star emits synchrotron radiation. And the optical synchrotron is just below, which is the masterpiece, which allows to see the supernova. You got to the point?
Yes, yeah. Otherwise, you wouldn't see it. Yeah,
You will not see it. And you don't care about the X-ray afterglow because it's not relevant.
Yeah.
This, to us, is the masterpiece.
Yeah, interesting. Yeah.
I hope you start to feel it.
Yeah. I'm getting there.
The more you see it, the more beautiful it is. Are you there?
Yes, I'm listening. I'm thinking about it. I have to study your paper more carefully.
Yes, there are not one paper. There are some 10 papers right now. Therefore, we have to write a review of all these things because we have been working enormously. And we are just... but now let me go to, if you don't mind, let's go to a BDHN1. No, we are in BDHN1, where you have the black hole, okay? Tomorrow, I don't want to spoil the talk of Wang Yu, but let me show you when you have a BDHN2, you have a new neutron star spinning much slower than in the BDHN1.
Mm-hmm.
And maybe we have one of these plots. One you will show tomorrow, maybe it's better we leave it there. But let me touch on something which is which we have to touch with you. Okay, you will hear tomorrow from Wang Yu. Anyway, when the spinning of the neutron star is lower, then the supernova goes over the X-ray, and you see it regularly. You don't need miracle, like in the BDHN1. In the BDHN1, you have this miracle that the synchrotron help, but in the other case, you don't need. Okay?
Okay.
Let me touch for you on a different point. Let's go back to the previous slides. Raim, the one with the different event, the different event. Okay. They are all the GRB, okay, we have considered are in the range Z smaller than 1, because we like to have the correlation with the supernova. Okay? Are you there?
Yeah, yeah.
Now, on the other side, if you look at the different events of a BDHN1 of this kind, you have 7 different, just a second, sì? Sentiamo dopo, stiamo parlando. Sì. Okay. Are you there?
Yeah.
We have what we call the 7 seals. We have, on a typical BDHN1, you have 7 seals, 7 phenomena. UPA1, UPA2, the new neutron star rise. I cannot go into details. The flare, the X-ray flare, the gamma ray flare, and the X-ray after. You have 7 different seals, event, characteristic by spectra. Okay? Plus 2 afterglow X, optical, and JEV radiation.
Mm-hmm.
Okay? So this is a typical BDHN.
Yeah, it's
Okay, are you there?
yeah. So you're in a way just combining all the possible radiation in one model, the afterglow and optical X-ray and prompt and this.
But they have 7. Now, don't forget, the most general BDHN1 has 7 seals. We found all over this, okay? On all BDHN1. There are hundreds. Therefore, we have checked that. And they have this, each one with its own spectra. This has been the masterpiece of Liang Li. He's unable to, he's the best statistical person in the world, but he has capability of spectral analysis, but the overall picture he does not enjoy as much as we do. And we use a spectral analysis, which is reproduced. Are you there?
Yes, yeah. Well, I think that's a good approach to more physics related.
Okay. Now, let's move to Z equal 4. (220101). I hope you will be able to show you the slides tomorrow, or otherwise we have to organize tomorrow evening for you. But let me tell you the most fantastic part of the story. Are you there?
Yeah.
When you go to Z equal 4, you can do all the spectral analysis. But of these 7 seals and afterglow, 2 afterglow, the one in the JEV and the one in the X-ray, survive. Let's leave the picture on because we need the picture. But the statistic, the number of photons, can we have the image again, Raim? But of the 7 seals, there is only one surviving. The new neutron star rise, the number 2. And the other one, since the number of photons is not good enough, you cannot distinguish them. And many of these seals coincide only with one. This is the thing you were mentioning, that in your article, that as you become weaker in the source, okay, you lose information.
Yes, yeah.
And therefore, some of the seals, you cannot find them any longer. And you have only one which sums up 4 of the seals, but the T90 decreases. Are you there?
Yes, that naturally happens when you go to higher redshift, yes.
Exactly, but this is very interesting.
Yeah.
We show that. We show exactly what happened. And to me, the most exciting part, by far most exciting, is that you go to z equal 8. Are you there?
Yeah.
And at z equal 8, there is only one seal left.
Just the prompt, huh?
If you like.
Yeah.
No, one seal left. This, to me, is fantastic. I am very, very excited about that. This is the reason why I invited you to come in person, because we have to, this has tremendous consequence in cosmology.
Yeah, I'm sorry I couldn't make it. Yeah.
No, it's okay, but we have the great fortune to speak today.
Yeah, good.
I think you got to the point.
Yeah, I whet my appetite now to study him some more.
You see the point?
Yeah, I see the difference between this and sort of conventional model. That's great. Great.
Yes, but the conventional model does not take into account many, many things. They just speak about jet. But jet, they are synchrotron and so forth and so on. But in addition of that, you have to take measurability, number of photons, statistics.
Mm-hmm.
And you have depletion. This is the most important point, depletion of information.
Yes, I agree. That's a very important thing to consider.
And in a certain sense, it's like, if I may say so, that nature, I tell you in the most paradoxical way, nature is trying to hide what is going on at IZ.
Yeah, in addition, I would just add, in addition to losing signals, temporal characteristics also start changing.
Completely.
Yeah.
This is the key point of our article. But should be worried. Now, let me tell you, I hope some of you will follow. This is much more general statement. Should be worried about this. And I don't think so. I think the crucial point is that we have understood how black holes work. with z equal 1, smaller than 1, this diagram, we have discovered the 7 seals. Okay?
Mm-hmm.
And we have discovered them for z smaller than 1. Of course, we lose them. But who cares?
Devo dire che se tu hai, cioè se tu un tiro BAM, no?
Cos'è?
Sorry, I had the mic open, sorry.
Chi è?
No, in Francesco Longo. Sorry, I had the mic
Francesco,
open.
stai seguendo, è molto delicato il discorso.
I'm following, yes.
But we should not be worried. Because the physics we understand on GRB at z smaller than 1 is the physics of black holes independent on the mass. Therefore, the GRB data are the one which allow to understand black holes as z smaller than 1. And the same physics, this is the masterpiece of the work we did with Orge, the same physics applies to maxi black hole in artigalactic nuclei. But without the GRB and the machine, the inner engine, we could not understand the M87. Therefore, GRB have been essential in understanding black holes. And then we can use them at z equal 10 in artigalactic nuclei. This is my great message. But this is due to the work Orge did with the scaling. Well, these are my summary. I don't know if you have followed.
Some of it, not all. I need to more detailed study. I don't know about other people, but.
Well, the paper are published. We will summarize them. We will methodically refer to them, but the results have been obtained. And the picture is fantastic. Complex, I don't deny. I mean, there is a huge amount of physics which nobody has been able to do yet, because we had the fortune to have some key idea developed with Jim Wilson, the electron-positron acceleration, the optically thick, all this part we did with Jim. And this is partly done also by the traditional model, but we have enormous difference because they have one object doing one thing, instead we have object time varying on very different time scale and different physics. Francesco, hai sentito?
Sorry, could you repeat? I haven't, no, I was aside for a second. Could you repeat?
I repeat that we have analyzed all the physics of black holes with the 7 episode, this 7 episode, okay, for z smaller than 1.
Yes.
And we have identified, as we move to IZ, the number of episodes diminish until they practically shrink to 1. Therefore, we cannot work at higher Z. But the point is the physics which we understood as z smaller than 1 apply as well with the due scaling to artigalactic nuclei. Therefore, we can, thanks to the understanding of the inner engine of black hole, we can use the same equation that we have learned, the inner engine with the effective charge and so forth, also for artigalactic nuclei. And therefore proceed to understand at very high Z the physics of black holes. But we could not have done this if we not understood the gamma ray burst at Z smaller than 1. We can proceed to larger black hole just by scaling of the same law. But we have learned the law for Z smaller than 1. This is the beautiful paper we publish with Jorge Rueda.
But Remo, sorry, but the main difference between GRBs and AGNs is that AGN flares somehow repeat in big black hole, the one, let's say, that are hosted by active galactic nuclei. Instead, GRBs, as far as I know, didn't repeat, so they are just once.
Exactly.
Before.
But
So,
the physics, yes, thank you for this question. Yes, but the physics, forget about the phenomenology that the GRB lasts very short, okay? 100 seconds. But the physics we learn about the extraction of rotational energy during this 100 seconds, okay, is the same physics which apply on a steady situation in active galactic nuclei. The extraction of rotational energy is the same machine. Of course, in active galactic nuclei lasts much, much longer because the use of the rotational energy can go on for a million years. But the physics, this is my point, the inner engine is the same. In GRB lasts much short, 100 seconds, but the physics we have learned about the energy extraction is the same. You just scale the mass, the magnetic field, but the acceleration process is the same. I understand that this can come as a shock, but this, I think, is the most important result, which is intrinsic in our paper with Rueda.
okay, understood.
Understood?
Yes, yes. And the papers are the one, let's say, that you wrote with Jorge, yes. Okay.
Yes, the one in where the scaling are written.
There's one in astronomy and astrophysics of last year.
Okay, thanks, Jorge.
But what to me is, I ask Vai to be with us, is that he was the first one to point out how critical is the variation of a GRB with distance. And it's a fact that almost is like if nature wants not to tell us how to approach LRZ with the GRB. But we can use all the information on GRB, keeping going with artigalactic nuclei. But we can understand artigalactic nuclei only because we understood the GRB. And of course, in M87 and so forth, okay, let me touch on, excuse me, I need to tell you something more on this. In M87, in GRB, the time scale of the repetition of energy extraction, are you there? This is a very important concept.
Yes, sir.
The energy emission, which has been shown by Rahim, to work around black holes of 3 solar masses is 10⁻⁹ seconds. the repetition time, okay, in the UPE. Are you there? This was shown by Raim this morning. But when you go to 10 to the 10 solar masses in M87, 10 to, or more, this 10 minus 9 seconds becomes 30 minutes. And this is the flaring that you see in M87. But the mechanism, the physics is the same, just by scaling. And this is the beauty of this field, scaling. Therefore, somebody can say, oh, but how can you say 10 minus 9 seconds? Well, of course, detect by all this beautiful result that we did with Wang about self-similarity. But in the case of M87, this 10 minus 9 seconds become 10 seconds. And therefore, you can see the beauty of vacuum polarization with magnetic field much smaller than the critical field, but still working on a longer time scale. Therefore, this is the beauty. And this is the beauty of the physics of GRBs, of black holes, that you can use both GRB and active galactic nuclei. I hope you got to this point. Francesco, è chiaro?
Yes, yes, yes. I thought that you were asking to anyone. No, just
yes, me. And also to Vae. You got to this point, Vae?
Yes, yes.
I mean, the papers are there. It will be quite difficult to, we will make an effort in writing review, and we will need your help to make sure that what we write is clear, but we will dedicate some time in putting all this and giving the correct reference and the way that all this work has been developing.
Yeah, yes, on this point, I would like to add something about this complexity. Well, we are aware that somehow we have not been friendly friendly enough in our papers.
Excuse me, I did not understand.
That in our papers we have not been friendly in the presentation of some of the problems, because they are some have a complex that needs to be treated with numerical simulations and some of these points. But we now are making an effort to extract what are the main points and to formulate some at least semi-analytic formulation of the main points for the physics of variation, starting from the accretion process. So we are getting some analytic formulation for the spinning up, for the spin down, for their approaching the critical mass black hole formation. And we have been making the same for the UPF phase, making some semi-analytic formulation for the transparency of the pulses of the UPE phase. And the same we are making for the GeV emission and for the synchrotron, for the multi-wavelength synchrotron, so the X-rays, optical, and X and radio emission, trying to get an analytic formulation of all the pieces of the model in such a way that people can even approach to our model and get used to it more friendly. So we are also I think this is important. This is an important point.
I am absolutely fascinated by your wording, because we have been working day and night under all possible circumstances, guided by the physics and obtaining the result like Fermi did as quickly as possible. Fermi was not too kind in the way that you are mentioning. he did with the first computer the work about the black body radiation in cosmology, in quickly using the computer in a few pages, and people copied that over and over and over without giving reference to him. But we do like Fermi, and when Fermi used to need an integral, he was, I did an integration once using the square on a piece of paper. I showed to Wheeler, and Wheeler said, "Oh my God, you have done like Fermi." Fermi was supposed to make an integral, and he took a piece of wood and then he weighted the image and find the integral. Yes, we have been working not very friendly. You are right, but we have obtained the results. And I feel quite confident that already the material, all the material is expressed sufficiently. But I agree, if you have the courage to make more friendly, I admire even more, because you are the only person who can do that. And I'm sure we are we need to do also this.
Yes, we need to do all this and write them.
But with your help, I am insisting, Vae, I'm insisting, Chris, I'm insisting, Francesco, I'm insisting, please help us, because Yerlan, Raim, Wang Yu, Yang Li are working very much, but we need especially Giovanna,
Yes.
Specialmente Maria Giovanna, help us, okay, because we have done this. Now we need with your help, to explain and to fit. And you are in a fantastic position there to have access to data and so forth. But I would like also to invite you to spend, we have this visiting, we don't have money, we have little money, but we have established this adjunct professor in ICRANET, which is working, in which we bring people like Carlos Arguelles from Australia. We are planning to have, where is she? Disappeared. The speaker, Laura, soon, and so forth. A period of 1 month or 2 months with us can be very beneficial to us and to you. Please keep that in mind.
Okay, thank you so much. Thanks.
Okay.
And Pescara is a nice place to stay also.
Yes. I've been just to the beach today for 1 hour. Yes. And it was really very nice.
Okay, so I guess if there is no more ongoing discussion, and of course I'm sure we can continue the discussion tomorrow, I think we can close this session. So thank you very much all, and see you tomorrow.
Thank
Bye.
you all of you.
Bye.
Thank you all. Goodbye.
Ciao.
Bye bye. Ciao a tutti.